Introducing Yolanda, Eyducia Silaban from Medan State University. In this project video, I present an elastic material with negligible mass. Elasticity is the ability of an object to return to its original shape when a force is applied. One of the elastic objects is rubber, and I will use rubber in making a simple elasticity system in this video. For the tools and material that will be used in the system, I use a ruler, a hook, 2 pieces of rubber, this bottle that is, I'm fill this bottle with water as a weight. The mass of the bottle and the water is 250 grams. Okay, first I will assemble the system, namely by tying the 2 rubber knots. And then I will hook one end of the rubber to the hook. Then measurements are made of the initial length of the rubber. We can see length of the rubber from this ruler. So the length of this rubber at first is 5 centimeters. After that, the second rubber band is tied to the bottle, which has been filled with water. And then I will hook it back to the hook. We hook it back to the hook. Next, the question is, how can this system move? So, when the rubber, which is an elastic object, is given a load, the rubber will increase in length. And when the system is given a deviation that exceeds the equilibrium point, and then we release it, the rubber will experience back and forth movement due to the restoring force whose direction is opposite to the direction of increasing length of the system. We can write Hooke's law equation is force equals to negative k times the displacement of object. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. From the system, we can see the case, namely if the rubber moves in balance and if the rubber moves in oscillation. In both cases, the rubber degree of freedom is an ideal degree of freedom. Okay, for the first case, namely the rubber moves in equilibrium, we will see how much the length of the rubber increases after being loaded. For the example from the system, the length of this rubber at first is 5 centimeters, and when we add this object, the rubber increased the length, and now the length of this rubber is 16 centimeters. So for the equation for this case is sigma force is equal to 0. We can write this equation to be minus k times displacement of object minus mass of the object times gravity acceleration is equals to 0. From this equation, we can get the equation of this displacement of the object is equal to mass of the object times gravity acceleration divided by k. Okay, next, the second case, the rubber moves in an oscillatory manner. Oscillation is the back and forth movement of an object past the equilibrium point, which is caused by the presence of a restoring force. This happens when I apply a downward force on this system, that is past its equilibrium point. Then I release it. We can see that the system will experience oscillation, that is the movement is back and forth. So if we were to graph the position of the object against time, it will describe sinusoidal behavior just like a trigonometric sin function. So that's why the equation of oscillatory motion of rubber and spring can be written as y equals to the amplitude times sinus in bracket omega times t plus minus k times the displacement of object. I will sketch the graph of the position the object against time. So this is the graph of the position of the object against time. We can see that this graph is like a sin function of trigonometry. Okay, the next, for the other equation that you can use for this case is sigma force equals to mass of the object times acceleration. Then we can write as k times displacement of the object equals to mass of the object times d square x divided by d square. And we get omega equals to root k divided by m. The k is the constant of the rubber or spring, and m is the mass of the object. From this expression, we can see that omega is equal to 2pc, 2p divided by t, or divided by the period. So the equation we can write as 2p divided by the period is equals to root k divided by m. From this expression, we can get the expression of the period. That is t equals to 2p times root m divided by k. And from this equation 2, we can get the expression of the frequency. The equation of the frequency is frequency equals to 1/2 p root k divided by m. So this is the equation that we can use of the both cases. This is for the case that the rubber moves in equilibrium, and this expression is for the rubber moves in an oscillatory manner. So next, the problem with this system is that the large downward force of the gravity can damage the oscillatory motion. Apart from that, another obstacle is that applying downward weight force is not in a straight line with the rubber hook point. This can also disrupt the oscillatory motion of the system. Okay, so that's the material I convey in this project video. I hope you like it, and thank you.